velocity always zero? And I said, yes. And I was wrong, because if something is kind of overpowering, like if I'm running towards a, I don't know, basketball that's bouncing towards me, and one of us has a spring on it, I'm going to overtake that thing. Unless it was shot out of a cannon, I'm just going to take it in stride. So we can both be moving same direction while the spring is compressed maximum to maximum effect before it kind of launches out. Does that make sense?
Yeah.
So it's not like both come to a stop and then both go in the other direction. If one's bigger and will continue on in the same direction, then yeah, the velocity is not zero during maximum compression. So just wanted to mention that. Um, Gavin, can you see this in the bottom of the screen? Oh, it's gone. Never mind. You can see the notes, right?
Yeah.
You're breaking up. Hopefully this is going to work. Let me know when you got this down, pretty please.
Okay.
Okay, glancing means they're at an angle to the original momentum. All that means is that they're not kind of like in a straight line, train track style, like where one hits and then either they both move away from each other or what have you. There's going to be an angle involved, which is why we're going to do vector addition, but we're doing it with momentum, and that changes things a bit. We'll do an example. The note here, watch for canceling vectors off the original line. I'll let you write this down, then I'll talk about what that means.
Okay.
Okay, so stop my sharing. So when I was saying about how the vectors kind of cancel off the original line, what I'm talking about, here's an example. We're not going to go through it. I think you'll be able to on your own. But generally speaking, what's going on here is, so this curling stone hits the green curling stone. The green one's going to go down and to the right. The blue one's going to go up and to the right. These are the resulting kind of movements. When I'm talking about canceling, the vertical component is going to be the exact same as the vertical component here, except to the negative. One's negative, one's positive. Otherwise, they're exactly the same, because there is no kind of vertical velocity or momentum. Final has to equal initial, so those will cancel out. It's going to be the total kind of going this way that equals this. Does that make sense?
Yeah.
Yeah, so just watch for those glancing. That's what that one's all about. Have a look at sample problem 1 at your leisure. I am going to do practice on page 252. Just gotta find a place to put my book. My desk used to have lots of space. I need to make some changes. All right. Get out of here, cord. Okay, so page 252, number 1. Two freight trains have a completely inelastic collision. One way to remember kind of which one's elastic, which one is inelastic. Think of elastic as kind of bouncing off. Inelastic, they stick together. So it means that these trains, when they hit, they are staying together kind of for the remainder of their motion. Two freight trains have a completely inelastic collision at a track crossing. Engine 1 has a mass, okay, so M1 equals 1.4 times 10 to the 4, 1.4 times 10 to the 4. This is in kilograms. Yep, that's good. Traveling 45 kilometers an hour, V1I equals 45 kilometers an hour, and it's going north. I'm just glancing at the answer, and it's going to want it in meters per second, so we're going to have to convert this. To convert it, 45 kilometers, so it's 45,000 meters, 45,000 meters divided by, and it's per hour, need to change that to seconds, 60 times 60, that's 3,600. 12.5, well, that's a nice even number. So 12.5 meters per second north. M2, 1.5 times 10 to the 4, so 1.5 times 10 to the 4 kilograms. And V2I is 53 kilometers an hour. Which way is this one going? This one's going west. Holy moly. It's not a good train situation. That is 53,000 divided by 3,600. 14.72. Okay, so we've got M1, V1, blah, 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 blah. Calculate the final velocity. Okay, so this is, actually, let's figure out, so momentum for the first one is M1 times V1, which equals 14,000 times 12.5, 175,000. Second momentum, M2, V2 is 15,000 times 14.72, 220,800. Does that make sense what I'm doing so far?
Yeah.
Okay. So this is where the vector addition comes in. So this first one is going north, right? Yeah, this one's going up. This one's going to the left. Who's texting me? My wife. Wait. So we do 1, and that one's 175,000, and then one's going this way, 220,800, and so we solve for that. So a squared plus b squared equals c squared, 175,000 squared plus 220,800 squared equals c squared. That was already in my calculator. Okay, I'm going to do this in one step just because it's really big.
Yeah.
So let's just, the root of that equals the root of that. So 175,000 squared plus, just be careful with your calculator how it interprets these things. Squared equals this, then I'm going to take the root of that. 281,740. So that equals c. That's the momentum, excuse me, for the kind of final momentum. What is the question asking? Final velocity. Okay, so we have the final momentum. Now, to look at it one way, M1 VI 1 plus M2 VI 2 equals M1 VF 1 plus M2 VF 2. Right now, we have the total momentum of this whole side. That's what this is. So if we, and also the speed is the same because it's an inelastic collision. So this is essentially, so 281,740 equals M1 plus M2 times VF. Is that okay so far?
Yeah.
These two masses we have, that's like the 14,000 and 15,000, so that it equals 29,000. So we just divide both sides by 29,000 to get VF. So VF is divided by 29,000, 9.7 meters per second. That's the final velocity. Actually, that's the final speed. To get velocity, we need to get the direction. So I'm going to get it from here. So that's odd. So theta equals inverse tan of opposite, which is 220,800 to 220,800 divided by 175,000. No, I'm in gradients, or radians, I mean. Now in degrees, so second tan, open bracket, 220,800 divided by 175,000, 51.6, so 52 degrees. So it's going to be north 52 degrees west. Hopefully that lines up with the book. It does. Does that make sense?
Yeah, that does.
And you're able to get everything that I showed on the screen here?
Yeah.
Okay. Oh, I should have made this bigger. I'm just realizing my own, because if I'm recording the screen here for everybody, all two of the other hosers, I'll just get a fuller view. Although, I guess you were able to see the full view, right? Like nothing really changed for you right now?
No.
Okay, yeah, it's just changing on my screen, but my screen's what's recorded, so hopefully this makes sense. And if you're good, Gavin, then we're good. That's it till tomorrow.
All right. Thank you.
All right, have a good one.
You too.